Sliding down a rough inclined plane. A block with mass 5 kilograms slides down a surface inclined 36.9 degrees to the horizontal. The coefficient of kinetic friction is 0.25. A string attached to the block is wrapped around a flywheel on a fixed axis at O. The flywheel has mass 25 kilograms and moment of inertia 0.5 kilograms meter square with respect to the axis of rotation. The string pulls without slipping at a perpendicular distance of 0.2 meters from that axis. Part A, what is the acceleration of the block down the plane? Part B, what is the tension in the string? Okay, so let's start with the free body diagram of the 5 kilogram block. So we're going to see the weight of the block pointing down, mg. There will be a normal force from the inclined plane. There will be a tension acting on it, and because it's sliding down, the kinetic friction would be pointing up. So let's put all of these together on this free body diagram. The weight making an angle 36.9 degrees with the vertical, the normal to the surface, we have a normal force, the contact force, the tension at 36.9 degrees with respect to the horizontal, and kinetic friction opposing the motion down the incline. And let's set up our coordinate axis so that the y-axis coincides with the normal force here, and the x-axis is in the direction of the motion. Okay, the net force on the y-axis, let's use Newton's second law here, must be equal to the normal force. We have the normal force. These two forces are on the x-axis, but this force has a component on the y-axis, mg cosine 36.9. So normal force minus mg cosine 36.9 degrees, and as a result of these forces there is no motion on the y-axis, so this must be equal to 0. Therefore we see that the normal force is equal to mg cosine 36.9 degrees. The weight of the block is 5 kilograms, so it's 5 times 9.8 times cosine 36.9 degrees. So we find that the normal force should be 49 cosine 36.9 degrees in newtons. The net force on the x-axis we can write is, first of all, due to the component of the weight on the x-axis, which is mg sine 36.9 degrees. That's in plus I hat direction, you can see here. And we have the tension and kinetic friction opposing it. Minus T minus Fk is equal to mass times the acceleration on the x-axis. And we have the kinetic friction Fk given by coefficient of kinetic friction times the normal force N, which is mu k mg cosine 36.9 degrees. So this is 0.25 coefficient of kinetic friction times 49 cosine 36.9 degrees, and Fk turns out to be 12.25 cosine 36.9 degrees in newtons. So I'm keeping the cosines and sines to get the final answer correctly with the right number of significant figures. Okay, so going back to this force equation on the x-axis, we have mg sine 36.9 degrees minus mu k mg cosine 36.9 degrees minus tension is equal to mass times acceleration, and we obtain 49 parentheses, because mg is 49, 5 times 9.8, sine 36.9 degrees minus 36.9 degrees minus mu k 0.25 cosine 36.9 degrees is and minus the tension here is equal to mass times acceleration, which is 5a. Now let's call this equation number 1. Now I want to concentrate on the flywheel. The flywheel has a weight. There will be a normal force from the rotation axis it is sitting on, and there will be a tension acting on it. So we have the contact force N, mg pointing down, and tension which is tangential to the flywheel. And we can see that there will be a net torque acting on it, which is equal to T times R, which is I alpha. And you can see for this to accelerate downward, this has to be rotating clockwise. So this will be the direction of alpha, so that it would be in minus k hat direction, pointing into the board. Okay, so if we multiply this equation with r, tr squared equals I alpha r, we know that alpha times r is linear acceleration a, and we find that the tension can be written as the moment of inertia times acceleration a divided by radius r squared. So tension times r squared, 0.2 squared, is equal to you can see here 0.5 times a. So the moment of inertia was 0.5, so it is 0.5 times a, and the tension is 12.5 a. This is our equation number 2, which we obtained using Newton's second law of rotational form for the flywheel. Now, putting equation 2 in equation 1, we have mg sine theta, minus mu k mg cosine theta minus the tension equals ma. Basically, that's the equation we have written here, where theta is equal to 36.9 degrees. And for the tension, I can substitute Ia over r squared, so it's mg sine theta minus mu k mg cosine theta minus Ia, the result I obtained from the torque equation, equals mass times acceleration. Isolating acceleration a here, we obtain the following equation: mg parentheses sine theta minus mu k cosine theta divided by m plus I over r squared. So if we substitute the numbers here, mg is 49, sine 36.9 degrees minus 0.25 cosine 36.9 degrees divided by 5 kilograms plus I, which is 0.5 kilograms meter squared, divided by radius 0.2 square. This gives us 1.12 meters per second square down the inclined plane. So that is our acceleration. All right. And in part B, we were asked to find the tension. The tension is IA over R squared. The torque equation gave us this result. So this is basically 12.5 times 1.12. So that gives us 14.0 newtons. So 12.5 we've obtained from I over R squared. So 0.5 divided by 0.04 gives us 12.5 multiplied with the acceleration A, 1.12, we find 14.0 newtons. Okay, let's summarize. We have this block with mass 5 kilograms accelerating downward on this incline under the influence of kinetic friction, which is opposing it, and the tension. And there will be a normal force for the contact between the block and the inclined plane. And this tension is acting on this flywheel and giving it a torque so that there will be no slipping and it will be rotating in the clockwise direction. Of course, there is the weight and the contact force on this wheel, but they don't create any torque effect. The torque equation will only come from the radial distance r here between the pivot point and the application point of the tension times the tension. So T times R is equal to I alpha, where alpha also creates, alpha is also in the minus k hat direction, so they have the same direction. So we have looked at the free body diagram of the 5 kilogram block. First, we write the equation on the y-axis, which is the axis normal to the inclined plane, and find the normal force. And mu k times the normal force is the magnitude of the kinetic friction, which is acting in a direction opposing the motion down the incline. So we know that this is the direction of the acceleration pointing down the incline. And the net force on the x-axis, on the motion axis, is the component of the weight on the x-axis, mg sine 36.9, minus tension minus fk, net force equals ma, Newton's second law. And we can obtain an equation for tension in terms of A from this diagram. And from the torque equation, T times R equals I alpha. If we multiply both sides with R, we obtain alpha R, which is equal to linear acceleration A in rolling without slipping. So it's rotation with no slip here. And this is going to give us T is equal to IA over R squared. So combining these two equations, 1 and 2, we can solve for acceleration A. And then we can substitute the result into IA over R squared for tension, and we obtain our tension on the string.